have some of your corrected homework here. Homework 9 is there. I don't yet have homework 8, but I should have it. I can return it on Tuesday, which will be our last lecture. I did post the exam in case you didn't notice, so it's up there. Due a week from Tuesday, we said? Yeah. And all the instructions are there. So today's lecture will be a bit on the short side, and that will leave us time for passing back homework. And if you have any questions about the test, we could talk about them now. Or if you want to ask them privately, you could ask me. Better not to ask the TAs, because I don't want them to either give answers I wouldn't agree with or help some people more than others, whatever. So yeah, just direct them to me. All right. So let's begin here. We're talking about strange attractors and their fractal substructure. So we looked at the Lorentz system last time, and well, not so much, did we? I mean, I guess we talked about the Rossler attractor, and then we gave this intuitive picture that I described in terms of dough and pastry and flaky layered structures. Pretty flaky lecture, actually. So maybe we should try to make that more visually convincing. That's what I'm going to try to do today by talking about an example known as the Hénon map. So you can read about it in section 12.2 of the book. And so the work was done around 1976, published then. Michel Hénon is a French mathematical astronomer who was apparently at a lecture by another French physicist named Yves Pomeau, who was talking about the Lorentz system in the days when the Lorentz system was extremely hot. Remember that, you know, it was published in 1963. It was ignored for about the first 10 years of its life. And then by the mid-70s, people had sort of discovered it and were fascinated by what Lorentz had seen, and they were going much deeper. So anyway, Pomeau was introducing this to his colleagues, and I think he was specifically interested in the point where Lorentz, which we read last time, that quote, where Lorentz says it's not really a surface, the Lorentz attractor, it's an infinite complex of surfaces that is made of infinitely many sheets packed together very closely in a certain way. And so Pomeau was trying to describe that, and Hénon was sitting there in the audience and trying to visualize what he was hearing about. But Pomeau remarked that he couldn't really resolve these sheets that were supposed to be there. He tried numerically and couldn't see them. And so this gave Hénon the idea that maybe there's another way to try to visualize the fractal structure of strange attractors, and that led him to the work we're going to talk about now. That is, rather than deal with the Lorentz system itself, which has this extremely powerful volume compression, as we talked about. It shrinks volumes by a factor of about 14,000 after one circuit around the eye of the attractor, around one of the wings. So Hénon thought maybe I could make a simpler mapping rather than solving a differential equation. Let me do an iterated mapping, except instead of the kind we talked about earlier, one-dimensional mappings, he's going to create a two-dimensional mapping. And he wanted it to have adjustable amounts of contraction so he could see what was going on. So the Hénon map is a simple two-dimensional map that does have a strange attractor by design. And you'll see that Hénon's intuition is very similar to Rossler's about stretching and bending and re-injection. But I think their work is independent. Also, this map that we're going to discuss was, as I say, devised to illustrate the fractal microstructure of strange attractors. And really, it was the first direct visualization of something like that. first direct visualization of this predicted structure that Lorenz was talking about. Okay, so the map looks like this. I'll just write it down and then I'll explain how Hénon arrived at it. It's xn plus 1 is yn plus 1 minus a xn squared, and yn plus 1 is b times xn, where the parameters a and b are adjustable. Taken to be positive. Actually, they could be negative. It's whatever you want to do. So you've got a and b, and then, as you can see, it's a two-dimensional map. That is, an input would be a point in the plane xn, yn, and then this gives you its next iterate, xn plus 1, yn plus 1. And so you can visualize this as a point in the plane that hops to another point in the plane, and it will just keep hopping around under the action of this map as you repeat it. And so now, why this map? I mean, notice it's nonlinear because of this xn squared term, but that's the only nonlinear part to it. So it's minimal in the same way that the Russell attractor is, or Russell system was minimal as a differential equation. Only one quadratic nonlinearity in that one. But anyway, so Hénon got it by thinking about stretching and folding, as we described the other day. Stretching and folding of phase space. So let's build it up like this. Let's think first about a rectangle sitting in the xy plane. This will remind you of my blob that I was describing when I talked about the rolling pin. So there's our blob of phase space, or blob of dough, however you want to think of it. And then we're going to stretch it and fold it in the first step. So I'll have a sequence of transformations here, which I'm going to compose to get the ultimate transformation, that is the Hénon map. But let's label them with prime. Prime doesn't mean derivative, it just means this is the first one, t prime. So this is going to execute a stretch and fold. And it does it by taking this rectangular blob and mapping it onto these new axes that we'll call x prime, y prime. And we want the rectangle to be mapped into something that looks, well, it has a parabolic arc on the bottom and on the top. It looks like that on the bottom, and then also on the top. So you have taken the rectangle, stretched it, and bent it. That's its image. And the equations for it in this first step are x prime is equal to x. So you don't do anything in the x direction. But in the y direction, the new y is 1 plus y minus ax squared. And so you can see what that's doing is it takes a line. That is, if you think of this as being made up of a series of vertical lines, the x's are not changing on those vertical lines. They just stay wherever they were. But the y value, like if down here, if I had some negative y value, then I would feed in that negative y. Maybe I make it be less than 1. And then I do add 1 to it, so now it becomes positive. And then I do minus ax squared. That bends it into a downward parabola. And so that's what you're seeing, downward, two parallel downward parabolas. So this A controls the curvature, the amount of bending. All right, so that's the first step. Next, Hénon takes that and squashes it along the x-axis. Not totally squashes it, but just compresses it. The next step will be, we'll call it T double prime, which does a squash. So if you could imagine doing it with physical stuff, you'd just take your hands like that and go, you know, push it in. And so that map is very easy. We're just going to send, we'll make x double prime equal to a constant b times x prime. That is, we're just shrinking things in the x direction by a factor b. So b is going to be less than 1 in magnitude. It could be negative if you want, but turns out we're going to use a positive one. But anyway, the main thing is its magnitude should be less than 1. And y doesn't change. So y double prime is just y prime. And so the picture now looks like on the x double prime, y double prime axes, just push everything in sideways. So I don't know, maybe something like this. I have these vertical lines again that are the former sides of the rectangle. Then I draw some very skinny looking, well, that should be symmetrical, not so good. Let me try that again. Here's a skinny parabola that has been squashed. Whoa, that was supposed to connect to the bottom. Excuse me. There. So you're getting a boomerang shape like that. Any question about that? Adam, you look a little bothered. You're okay? Thinking about something else? Okay, so anyway, there's that. And now the last step is, oh, okay, so you may wonder, why are we doing this? I mean, why bother with the B? Remember that the Lorentz system has the property that it contracts volume. And so the analog here would be that we want a map that will contract area. And this first mapping, although it did bending, does not contract the area. You could show by computing the determinant that the area of this shape is the same as the area of that shape. So we did not do any area contraction yet, but B does do area contraction by a factor of B. And so this introduces dissipation in the sense of area contraction. And it also does a kind of extra folding or bending on top of what A did. So it does some additional bending. And then finally we said that we wanted to do a re-injection step. That is, we take the dough, we roll it out, we fold it, and then we put it back under the rolling pin. That's the re-injection part, where we start doing it all over again. And so here what we want is, since we had a rectangle kind of elongated along the x-axis, whereas this shape is now kind of elongated along the y-axis, Hénon decides he's going to rotate it, or actually he switches the role of x and y so that this now looks stretched out along the x-axis and is getting ready to be flattened and stretched and all that again. So the last step is, he doesn't phrase it this way, but in our terms, this is like the re-injection step, where we're going to just switch x and y so that the boomerang, or the horseshoe, whatever you want to think of it as, whoops, boomerage, no, that's not what I meant to write, boomerang, is elongated along the x-axis as the original rectangle was. And so that means we're just going to define x triple prime to be, that is this map, T triple prime just sends, makes X triple prime equal to the old Y double prime, and Y triple prime is X double prime. And that produces this result. Now we have that same thing, but looks kind of, well, let's see. So we used to have vertical lines, so now we'll have horizontal lines. And we used to have a large, had a positive Y double prime, so that's going to become a positive X triple prime. So it's something like this. Let's see, these guys have to become little horizontal pieces. So, I don't know, something like this, and then symmetrically like that. And then, what do? I go there up to the top, and then this goes around here. Well, I didn't get that quite right, but something like that. Ignore this. Anyway, so now it's bent like that. Or rotated around, inverted. Is there any question about anything in the series of transformations? Okay, so now the Hénon map is what you get by going from xy to x triple prime, y triple prime. And so we have to do the composition of these three mappings. That is, let's let x triple prime be what we're going to call xn plus 1. Y triple prime is what we would call yn plus 1. And we're going to let x be xn, and the original y is yn. And if you write it all out, then, well, so the transformation t of interest is do t triple prime after t double prime after t prime. And if you write that out, you'll get that t of xn yn is just xn plus 1, yn plus 1, given by what I wrote originally in the box. So that's how he came up with that map. And now what we want to talk about is the properties of this map. What are the interesting things about it? And, of course, what does it do? And what does the strange attractor look like? Did you have a question? No? Okay. So, properties. Well, I'm not going to show all the algebra to verify these properties. Please take a look at section 12.2 in the book if you want, but I'll try to explain most of them. Yes?
I'm just curious why Hénon has the plus 1. It's like a
Why the 1 in the first place? Okay, so the question is, why in the definition of the map does it say plus 1? It appears if we don't have that, then we have a fixed point at the origin. Now, I don't know if that would matter or not. I don't have a good answer for you. I have a feeling it's significant. That is, it's not just a gratuitous thing for some cosmetic reason. Yeah, let me think about that. I don't have a quick answer for you. But I do think it probably matters as far as what we're about to see. Okay, well, anyway, properties. The first thing to mention is the map is invertible. That is, given the point xn plus 1 and yn plus 1, you can go backwards to recover where it came from. Uniquely, you can solve uniquely for its pre-image xn, yn. And, well, why do we want that? Well, I mean, by the way, if you want, you can just check that by doing the algebra that you can solve. But it's important because remember that the Lorentz system, which we're trying to mimic, is a system of differential equations. And so given any point on a trajectory, you can flow time backward to get a point where it came from. And that is the analog of this map being invertible. Now, it's not true of the logistic map, as I commented in the last lecture, that in the logistic map, if I say, here's the logistic map, and then if I ask what point, here's a xn plus 1, well, it could have come from here or it could have come from there. And so you have a 2-to-1 map in the case of the logistic map. It's not invertible. And so in that way, it's not like what you would get from solving a differential equation, whereas this is much more like that. So that's one essential thing that's preserved by the Hénon map from Lorentz's case, an abstraction of what Lorentz had. Next, I mentioned it contracts areas. Let's see that. I mean, it's clear from the way it was constructed that it's contracting, but so like the Lorentz flow contracts volumes, so in that sense, the system is dissipative. Now, how do we know that? So there's something that you would have learned in a multivariable calculus course, or should have learned, that if you take an area and then map it, the ratio of the area after to the area before is the determinant of the Jacobian of that transformation. That'd be true for infinitesimal areas. And so I guess we could calculate that. Should we see what's the determinant of this thing? So the Jacobian, I don't actually have it written down here, but let's just do it. So we would look at partial of xn plus 1 with respect to xn, partial xn plus 1 with respect to yn, partial yn plus 1 with respect to xn, and partial yn plus 1 with respect to yn. This would be the Jacobian of the mapping, which, let's see. So from here we get minus 2a xn, and then differentiating with respect to yn gives us a 1. And then down here we're getting a b. And then yn plus 1 has no y in it, so we get a 0 there. And so the determinant is, it looks like, negative b. And the thing is that the ratio of areas is, if you consider them as positive areas, the ratio will be the magnitude of b. You may be wondering why we're getting this negative sign. That's related to that we flipped the axes in that third step. We inverted, sent x to y and y to x, so we changed orientation. But ignoring that, you see that if b is less than 1, areas contract. So that's why he's going to choose b less than 1. Also notice it has a constant determinant. So areas are shrinking at the same rate, at a constant rate. That's analogous also to the Lorentz flow, which we showed had a constant rate at which volumes shrink. That is, dv dt was, well, they're shrinking exponentially fast, but I mean in each time step they shrink by the same factor. Similar to this. Any questions so far? Okay, so then what else? Another key property of the Lorentz system is that we said there was a trapping region, that there was a big ellipsoid, or you could use a big sphere, that once you get into that sphere, you never get out. And the Hénon map has something similar. It has a trapping region too. It has a trapping region that contains the ultimate, the strange attractor. But there's an important difference between the Hénon map and the Lorentz system, which is that the Lorentz attractor is a global attractor. Any initial condition, except ones that lead to saddle points or saddle cycles or whatever, but except for those exceptional initial conditions, almost all initial conditions go to the attractor, no matter how far away you start. That's not true in the Hénon map. The Hénon map doesn't have a global strange attractor. You can see that by just thinking about the map. Well, I guess I've erased it. But remember it had an x squared term in it? So if x is big, then the x squared term makes the next iterate even bigger. And so actually things can escape to infinity in the Hénon map. If you start far enough away from the origin, you can get out all the way out to infinity. So not all trajectories or orbits here fall into the trapping region. Not all the orbits fall into the trap. So unlike the Lorentz system. Because some escape to infinity due to the x squared term. So, but there is a trapping region, and let me draw a picture of it for you. Yes?
I had a question actually about number one.
About number one?
Yeah.
Okay, map is invertible, yes?
Since there's an x squared term,
Doesn't seem like it's unique. Should we crank it out? Let's just check.
well, I was just wondering if it
Yeah, you'd worry because of the x squared. And that may have something to do with why the 1 is there. Back to the earlier question, wherever you are. Yes, there you are. Thank you. So why don't we just invert it manually, just to verify this. Actually, while I'm on this point, though, let me show you the trapping region. Then let's go back to verify that it really is invertible. Okay, so what does the trapping region look like? Hénon computed one analytically by drawing an interesting quadrilateral. It's sort of looks approximately like this. You go from minus 1.5. Oh, I didn't say, but in his work he chose the parameters a and b a certain way. So from now on we're going to assume b equals 0.3 and a equals 1.4. So those are the standard values used, and I'll explain why he chose them in a couple minutes. So we'll come back to that, but anyway, he chose them, and with that choice, then his trapping region looks like so. We said we're going from 1.5 to negative 1.5 on the x-axis, and say about 0.6 to negative 0.6 on y. And there's something that looks about like this. I have the actual diagram from his book, his paper in the book, but it's it's not an obvious shape. Sort of about like so. So there's some funny trapping region like that, and what happens is if you take this region R, and then it's bounded by these 4 straight lines. If you then map those straight lines using his map, you can show that the shape ends up looking about like this. So that is this region in here that I'm going to shade. This is the image, T, the transformation applied to R is that boomerang shape, and it sits inside R itself. So you map R into itself, into this shape, and we'll see that when we run the computer simulation in a couple minutes. But anyway, so R does get mapped into itself, and in that sense, once you're inside of R, you can't get out. Now back to Adam's question about the invertibility of the map. Let's just quickly calculate to see if it is invertible. It's supposed to be. I don't have it in my notes here, so be careful to check me on the algebra. I could mess this up. But let's see. So we were saying the map is xn plus 1 is yn plus 1 minus a xn squared, and yn plus 1 is b xn. And so what we want to do is solve for xn and yn, right, given these. Okay, so I can certainly solve for xn in terms of the future value yn plus 1. It's yn plus 1 over b. That's good. So I've now done that. And now that I've got that, I feed it in here. And yeah, okay. So now I have xn plus 1 is yn plus 1 minus a. Xn squared, though, I would write yn plus 1 squared over b. And the thing that's interesting here is notice the way that what has entered, I mean, this is what would have worried you. You were expecting this to be yn squared, in which case we would have a problem, because then we'd have a quadratic equation in yn. But it's not that. It's yn plus 1 that has entered. And so, in fact, it's easy then. You can just solve for yn. Yn is just, I mean, because that's what we're trying to solve. See, yn depends on the future in both x and y. So, all right, it's whatever. xn plus 1 minus 1 plus a over b yn plus 1 squared, if I did that right. Oh, b was supposed to get squared. Thank you. Good. Good save. So it is invertible. It doesn't seem to have had anything to do with the 1. That is this 1 that we talked about earlier. All right, but whatever. Yes?
It seems like without the 1, instead of opening compressing around 0, we would instead just get a spiral.
Oh, really?
So the 1 would be to give us that sort of opening compressing instead of a compressing spiral.
You're saying that if I didn't have the 1 here, you're saying we wouldn't get the kind of geometry that we've been getting. We'd get some kind of twisting. I don't know. I'm sort of slow seeing it in my head, and I don't want to do it now. If you want, we can look at it at the end. But let me jump to showing you some strange attractor pictures and stuff in the computer. Oh, I did want to say a little, though, before we start going into the computer simulations, about why why would Hénon choose these particular parameters? What's the motivation for those? And so on the question of choosing A and B, it's one of these Goldilocks things about, you know, not too hot and not too cold. If B is too small, say B close to 0, then you have very strong folding and squashing. Now, what's wrong with doing that? Or what's undesirable about that? Remember the goal of what we're trying to do. Yes?
You're trying to visualize it.
Exactly. We're trying to visualize the sheets of the strange attractor. So if you squash them too much, you're back to having the problem that Lorenz had. Everything is packed too close together and it'll be hard to see. So the sheets of the attractor will be hard to resolve. So you don't want to overdo it. On the other hand, if B is too close to 1, where the map is not contracting area very much, let's say in magnitude, then the folding may not be strong enough to produce chaos. So it was through trial and error that Hénon came up with this B of about 0.3, and it gave nice pictures. So let's now start to look at some of those. Yes? Your question is, how small does B have to be to produce chaos?
Yeah.
You would think maybe any B less than 1 should be enough. Yeah, I agree. It isn't clear why, how far down you need to go. I've posted some applets on the Piazza page that I found on the web, and some of them are interactive, so you can change the A and the B. So I guess I would just suggest, since I don't really know what the answer is to your question, just fool around with different A's and B's and see if you know what the pictures look like as you change them. It's possible that B could be bigger than the 0.3, but I sort of think you can't go too far from that and get nice pictures, though I don't exactly see why, just from having tried it. So let's see, I want to make the screen visible. There, not blank. And so here are some programs. I'm not sure which one to start with. Well, I don't know. Maybe, forget which one is good to start with. Let's look at this one. I think I got to do a little bit of, can't seem to find a scroll bar here. What's my attractor? Come on. Geez, I'm missing the whole thing. Maybe I'll start over. What if I go to this page and go back? Oh, great. Okay, it's not going to even do anything. I wonder if I'm not connected. I should be. Let's see how this one works. Well, there's some motion there. That's a good sign. And all right, so there's a little bit of a tutorial here. And he's conveniently drawn this. This is one where you see you can adjust. Oh, is it better with the lights out, do you think, Stefan? Okay, let's turn out the lights. So on this one, you have various buttons. You can change A and B. You can draw, if you want, 10,000 points or, oh, come on. All right. Huh. This hasn't happened to us so far this semester. We usually have pretty good results with these programs, but the red ball, the spinning ball of death appears to be getting us. Huh. All right, maybe we'll just try this again. Okay, here's one way of doing things. Just punish all these obnoxious programs by closing them. Ooh, even that's not possible. Okay, there, finally. Now, what if we go to our resources? And there's a final exam. Yay. And then down here, right. So here are the things that you can click on. Let's try again. Let's try this one. All right, that's the one I was just at. And, oh, come on. You're kidding. What? Go up. What's the matter with you? This is, who's doing this to me? Maybe I need my mouse. Not that that will help. I'm just stalling for time. Steve Jobs is doing it to me, the ghost of Steve Jobs. Nothing. Oh, geez. Maybe a computer reboot. It's a good idea. All right. That's always one way to go. That's rough. Okay. Well, yeah. Let's see. Okay, this might be a good time to take any other questions. We can come back. Anything else on your mind? Fine. I suppose I could. Oh. The airport icon?
Yeah.
Oh, really?
Yeah.
So maybe I wasn't connected at all. Here's one way of looking at the Hénon attractor. We could just go to his original diagrams. Can't really go too far wrong with that. So let's just quickly glance at what Hénon himself showed. That is, so he made these plots where he got pictures that look like this. That is, you're seeing there the strange attractor. It's this boomerang-y shaped thing, but you see it's got lots of thin wispies. And then to zoom in, he drew this little box up there. All right, there's this box. And if we then go to figure B, you can see what's in the box. I mean, from the scale you're looking at, it looks kind of like a thick line. But inside the box is B, and that'd be over here. And it's not really a thick line. It looks like, sort of like the rings of Saturn. I mean, there's this structure where it looks like there's 3 lines close together. Actually, naively, it looks like 1, 2, 3 lines of different thickness. But on closer resolution, you can see that one of them looks single, one of them looks like a double line, and one looks like a triple line. And then when you zoom in on the one that looks like a triple line, you get this picture, which shows that, again, that thing that seemed to be a triple line, 1, 2, 3, is actually a sequence of a thin line, a double line, and a triple line. And so you can keep zooming in like that. Those are the sheets. So, but let me jump out of there and see if I can get this to work in the computer itself by going back to our page. So here we are. No, that's the wrong course. That's my history of math course. Sorry. We're this. And resources. Good. I have a better feeling about this now. Okay. So let's try going here. And, oh yes, it's unsafe, but I'm going to risk it. Thank you. There. So you can play with this. But now, where was Hénon looking? I don't remember. But we could just, I think it was somewhere around the equivalent of this place. Whoops. Oh, I see. On this, what I'm supposed to do is just click, and then it will zoom in that part. So you see that little structure that we were talking about. And then you can see maybe, I don't know if the resolution is good enough. You get 1, 2, 3. I can actually ask it to draw more points. And then it starts filling in. You see that those curves are smooth along their length. The fractal structure is only in this transverse direction. And then again, where it looks like 1, 2, 3, zooming in, that 3 is itself made up of 3, as I can get by drawing more points. Okay, so it really is lots of sheets packed together in this interesting repeating way. Is there any question before I jump out of this program in favor of another? Yes? You say when you think about the Lorentz butterfly, that is the strange attractor that look like butterfly wings, this looks sparse to you compared to that. Well, so what you're remembering for the Lorentz system is that it looked like fairly solid wings, which, remember, of course, it's a three-dimensional system being projected onto 2 dimensions. And so you were seeing the wings, so to speak, like flat. And so they look pretty full of trajectories. But here, because we're looking at a 2-dimensional map, you should think of it as more like a slice through the wings. Now, the wings themselves are very thin sheets. And they're made, well, that's why they're often spoken of as a butterfly. Think of how thin a butterfly wing looks, not when you're looking at it face on, but the thickness of it, very thin. And it's, in the case of the Lorentz, it would not be a wing. It's many wings all packed close together, and those wings packed close together are analogous to these curves packed close together. So these are sort of like side views of the wings, if you want to think of it that way. I don't know if that's helping you or not. But, I mean, of course, it's not a perfect analogy to Lorentz at all. It's a different system. But anyway, all right, so let me jump out of this program and look at this one. This one has something that I've never seen anyone do before. I kind of like this. Oh, that is the one I was just looking at, sorry. Down here, this is a nice little idea. The creator of this program, who I guess is this gentleman up here, Robert Durner, has... You can maybe just see a tiny little circle of initial conditions. And then if you iterate them, they hop over somewhere else. And then they hop somewhere else. But they're getting stretched out. And as you keep going, they start stretching out more and more. Okay, this was, remember, just a little circle. As we keep going, you're starting to see them stretch out to form what looks like, they're getting spread over the whole attractor. And then a very cool move that is done here is to do a random initial condition that's just not one initial condition, but a big, scatter shot. So watch what happens after you iterate that once. Well, it goes into the it's in the trapping region, so it's going to make that shape. Right? And then as you iterate that, you start to see in this successive pruning that the attractor is emerging, from the successive iterates of that original blob. So it's fun to play around with. Anyway, I hope that gives you some feeling for what's going on. Yes?
Why did the original randomization result show that 4 of them are concentrated in the center?
The question was, why did the creator of the app choose to concentrate more dots near the center? It's a good question. It could just be that this is a random initial condition chosen from a Gaussian distribution in 2D. But I don't know. It could. Yes, do you have a suggestion?
I think it might be to just show you where it moves after the iteration.
To show you where this moves, so that is, if we iterate once, the dense region should be visible as something else that's dense. That's useful, right? Is that your idea?
That's an easy way to make a circle with computers. Uniform distribution of cards.
You're saying that if you just uniformly distribute it in R and theta? Oh, that's interesting. So you're saying if you pick a uniform distribution in R and a uniform distribution in theta and then plot it in polar coordinates, it will end up looking like this? Aha. That could be. So it could be that there's no particular strategy. I'm not sure. But anyway, it is sort of fun to watch the dense region move around. Here it appears to have gone there. Anyway, okay. So I'll let you fool around with that on your own time. And I think that's pretty much the end of what I wanted to say today. So let's leave it there. I do have homeworks to return to you if you want to pick them up. This is just homework 9, and I'll bring homework 8 in the next lecture.